Hello students, I am Dilip Udani, Assistant Professor at LJ Institute of Engineering and Technology. Today in improper integrals, I will teach you new topic, that is convergence and divergence of improper integrals. So let's start. So first of all, related to convergence and divergence of improper integrals, we have two tests. One is direct comparison test and second one is limit comparison test. So first of all, we will see direct comparison test. If f of x and g of x are two continuous functions for x greater than or equals to a, such that 0 less than or equals to f of x less than or equals to g of x, then integration from a to infinite f of x dx converges if integration from a to infinite g of x dx converges and integration from a to infinite f of x dx, that is less than or equals to integration from a to infinite g of x dx. If for x greater than or equals to a, this condition is satisfied, and if integration from a to infinite g of x dx is convergent, then integration from a to infinite f of x dx is convergent. And this also holds true, which is integration from a to infinite fx dx less than or equals to integration from a to infinite gx dx. If f of x and g of x are two continuous functions for x greater than or equals to a, such that f of x is greater than or equals to g of x, then integration from a to infinite f of x dx diverges if integration from a to infinite g of x dx diverges. If for x greater than or equals to a, this condition is satisfied and integration from a to infinite g of x dx diverges, then integration from a to infinite f of x dx diverges. So these two are conditions of direct comparison test. Now we will see limit comparison test. If f of x and g of x are two continuous functions for x greater than or equals to a, such that f of x is greater than 0, g of x is greater than 0, and limit x tends to infinite f of x upon g of x, that is equals to L, where L is between 0 to infinite, that is 0 less than L less than infinite. It means this L is a finite and non-zero value. Then integration from a to infinite fx dx and integration from a to infinite gx dx both converge or diverge simultaneously. If this condition, that is x greater than or equals to a, is such that f of x is positive and g of x is positive, and if you will find out this limit, and if you will find out this limit is finite and non-zero value, then if this integration is convergent, then this integration will be convergent, and if this integration is divergent, then this integration will be divergent. So this is all about limit comparison test. Now we will see examples related to direct comparison test and limit comparison test. Test the convergence of the improper integral integration from 1 to infinite cos x upon x square dx. Here fx is cos x upon x square. Now here we have selected gx equals to 1 upon x square. Cos x upon x square, that is less than or equals to 1 upon x square for x greater than or equals to 1. Because cos x is less than or equals to 1. So as cos x is less than or equals to 1, we have cos x upon x square, that is less than or equals to 1 upon x square for x greater than or equals to 1. Now we will find out integration from 1 to infinite g of x dx, and this is equals to integration from 1 to infinite g of x is 1 upon x square dx. Now we will replace this infinite by b. So this is equals to limit b tends to infinite, integration from 1 to b, 1 upon x square dx. Now we will integrate 1 upon x square with respect to x by applying the formula of integration x raised to n dx, that is equals to x raised to n plus 1 upon n plus 1. And 1 upon x square is x raised to minus 2. So its integration is x raised to minus 1 upon minus 1, and that is minus 1 upon x. So this is equals to limit b tends to infinite minus 1 upon x, and the limit is from 1 to b. Now this is equals to limit b tends to infinite. For upper limit b, minus 1 upon x will become minus 1 upon b, and then after for lower limit 1, minus 1 upon x will become minus 1, and outside we will be having minus sign, so minus minus plus, so we have plus 1. Now as b tends to infinite, minus 1 upon infinite tends to 0, and 0 plus 1, the result is 1. Therefore integration from 1 to infinite, 1 upon x square dx is convergent. Therefore by direct comparison test, we can say that integration from 1 to infinite cos x upon x square dx is convergent. Now this is example number 2. Check the convergence of integration from 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx. Whenever you have been given function of x like this, it means we have polynomial in numerator as well as polynomial in denominator. Then apply limit comparison test. Here function of x, that is equals to 3x plus 5 upon x raised to 4 plus 7, and we will select gx from this fx. Now see, the maximum power in the numerator is x, and the maximum power in the denominator is 4, and its difference is 3. So we have to select gx in this way. So gx, that is equals to 1 upon x raised to 3. Now limit x tends to infinite fx upon gx, that is equals to limit x tends to infinite. This is fx, that is 3x plus 5 upon x raised to 4 plus 7. Now we have to divide this f of x by g of x, or we will multiply this f of x by the inverse of g of x, and g of x equals to 1 upon x cube. So multiplying it by x cube by 1. Now this is equals to limit x tends to infinite, taking x common from 3x plus 5. So we have x into bracket 3 plus 5 upon x upon taking x raised to 4 common from the denominator. So we have x raised to 4 into bracket 1 plus 7 upon x raised to 4 into x cube upon 1 will be as it is. Now this is x cube and this is x raised to 1. So it will become x raised to 4, and in the denominator we have x raised to 4. So x raised to 4, x raised to 4 will cancel out, and this is equals to limit x tends to infinite 3 plus 5 upon x upon 1 plus 7 upon x raised to 4. Now as x tends to infinite, 5 upon x tends to 0 and 7 upon x raised to 4 tends to 0. So in the numerator we will be having 3 plus 0, and in the denominator we will be having 1 plus 0. So it is 3 upon 1. So it is 3. And this is a finite and non-zero value. So we can apply limit comparison test. Now we will find integration from 4 to infinite g of x dx, and if this integration is convergent, then we will say that the given integration is convergent by limit comparison test, or if this integration is divergent, then we will say from limit comparison test that the given integration is divergent. Now this is equals to integration from 4 to infinite, and g of x is 1 upon x cube. Now we will replace this infinite by b, so this is equals to limit b tends to infinite, integration from 4 to b, 1 upon x cube dx. Now we will find out integration of 1 upon x cube according to the formula. Integration of x raised to n dx, that is equals to x raised to n plus 1 upon n plus 1. Now we will write down 1 upon x cube as x raised to minus 3, and integration of x raised to minus 3 with respect to x, that is x raised to minus 2 by minus 2, and we will write down x raised to minus 2 by minus 2 as minus 1 upon 2x square. So this is equals to limit b tends to infinite minus 1 upon 2x square, and the limit is from 4 to b. And this is equals to limit b tends to infinite. Now replacing x by b, so we have minus 1 upon 2b square, then after minus sign. Now replacing x by 4, so minus minus plus 1 upon 2 into 4 square, and 4 square is 16, and 16 into 2, that is 32, so the result is plus 1 upon 32. Now as b tends to infinite, minus 1 upon 2b square tends to 0. So 0 plus 1 upon 32, that is 1 upon 32, and this is the answer of this integration, and this is a finite value. Hence integration from 4 to infinite g of x dx, that is convergent. Therefore integration from 4 to infinite 1 upon x cube dx is convergent. Therefore by limit comparison test, integration from 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx is convergent. So in today's lecture, we have gone through convergence and divergence of improper integrals. We have gone through the statement of direct comparison test, then after limit comparison test, and finally we have seen 2 examples related to this topic. Thank you for watching this video. I will see you in the next lecture.